Hi everyone, welcome back to sisyaclass YouTube channel. So in today's session, we are going to solve questions from general organic chemistry. We have learned this concept before also. I hope you have seen that session. I hope you have solved all those questions. We have covered the concept, how we have to solve questions in the last session. In today's class, we are just going to solve questions so that we can practice more and more as our exam is coming near, and more number of questions if you solve, your confidence will build up and obviously you will perform well in your examination also. Okay, so in today's session, we are going to discuss concept also. Don't worry. If I see a question on which you need some background information, I will give you that information and then only I will solve it, obviously. But we are not going to cover all the important points once again because we have done that already. So you can see our last session, you can go through it once and then you can continue with today's session in which we will solve questions. Okay, so let's start. Hello Prashant. So in today's session, we are going to cover general organic chemistry. All right. What else we are going to do? We are going to solve questions and we will learn about sorting concepts. Okay. So before we begin, I want to give you information regarding sisyaclass and then we will start with our past year questions. Okay. And again, if you have any doubt, you can ask me in the comment section also. And after the class also, if you face any doubt, you can post your comment. Okay. So I want to share one information with you that we are going to start with a maths 1 year program. It is for ₹999 only. So per day, the cost is less than 3 rupees. All IIT, NIT teachers will be guiding you, will be helping you, and the course is for grade 3 to grade 10, entire 1 year course in just ₹999. And if you enroll in the course, you can take help of Sisya AI also, in which you can solve your doubts. Text to text out solving, speech to text out solving, image to text out solving will be made available to you if you enroll in our course. So you can scan this code, download our app. The course will start from May 5th. So you can start enrolling. It is only for grade 3 to 10. Okay. So this was one information I wanted to give you. Now let's continue with our session. I will start with the content part. Before that, I want to introduce myself. So my name is Nidhi Narwal and we have been doing this EAPCET series for a lot of days and I hope you are following those sessions. I have secured AIR 32 in CSIR NET examination, and in today's session, we will talk about EAPCET. So I hope you have seen previous sessions also, so you know all about me. Let's begin with our session now. Okay. So what are we going to discuss today? We are going to understand questions based on it. Okay. We are not going to cover the entire concept once again. We will just solve questions. And if you face any doubt in any question, obviously you can ask me. Okay. So we will solve questions based on classification of organic compounds, the nomenclature, isomerism. So you have structural isomerism, you have optical isomerism, you have geometrical isomerism. We will solve questions based on that. Okay. Then finally, we will talk about reaction mechanism and how to purify such organic compounds. We will cover questions based on that also. Okay. So I hope you are following that and please solve questions alongside me. Try to solve it yourselves first. And after that, if you are not able to get the correct answer, then only see the solution. Okay. Don't try to just see the questions and answers and think I will do great. No, you have to practice yourselves also. So try it yourself first and after that you can see the solution. Okay. So let's start everyone. Let's begin. So first question, metamerism can be exhibited by the compounds containing. So metamerism is a type of structural isomerism. So what are the different types of structural isomerism? Let's revise them first, then we will solve this question. Okay. So you have learned about this, we have discussed in the last session also. We have the same molecular formula, but structural arrangement is different. Okay. So you don't have to cram this definition, but you just have to understand what do you mean by that. So there are certain compounds which have the exact same molecular formula, but their properties are different. Their structural arrangement is different. What do we call such compounds? We call such compounds to be structural isomers of each other. Okay, and within structural isomerism, you have further sub-classification. You can have chain isomerism, in which number of carbon atoms in your parent chain are different. You can have position isomerism, in which the length of the carbon chain is same, the type of functional group, the type of substituent is also same, but the position of that substituent, position of that functional group, that changes. Then we call all such isomers to be position isomers of each other. Okay, then you can have functional isomerism. So you have the exact same molecular formula, but the functional groups are different. Then we will call such compounds to be functional isomers of each other. Okay, then we have metamerism, for which we are talking about. So what do we understand by metamerism? And there are only certain functional groups which are going to show this kind of isomerism. So if you know about such functional groups, you can easily answer that question. So what type of functional groups will show metamerism? All bivalent functional groups will show metamerism. What do you mean by bivalent functional groups now? All such functional groups which are connected to your alkyl chain from two different sides, bivalent. There is a functional group which is connected to two alkyl chains, on two sides. We will call such type of functional groups to be bivalent functional groups. Okay, so for example, ether, it is connected to your alkyl chain on two sides, right? Bivalent functional group. Ester, it is connected to your alkyl chain from two sides, bivalent functional group. Bivalent functional group. So like that we can classify the metamers. So how do we understand that they will show metamerism? If the type of alkyl group is different on both sides of your functional group, then we will call all such compounds to be metamers of each other. For example, you have this kind of ether. On one side you have methyl group, and on the other side you have the propyl group. That is one compound. Now I will write another compound with the same molecular formula. That would be the metamer of first one. Okay, so in this case, please notice I have written ethyl group on both sides. So what do we call these two compounds? We will call these two are metamers of each other. So this is how we can understand metamerism. It is shown by bivalent functional groups. Now can we answer the question that was asked? Please see. Metamerism can be exhibited by the compounds containing monovalent functional groups. For that, monovalent functional groups like your alcohol, your aldehyde, your carboxylic acid, all such normal functional groups which are connected to your alkyl chain on one side. They will not show metamerism because you need two different alkyl groups on both sides. Correct? Two different alkyl groups must be connected to your bivalent functional group. Then only you will call such compounds to be metamers of each other. Right? See? Here there was methyl and propyl. Now we are writing ethyl and ethyl. So the type of alkyl groups are different. So these two are metamers. For that to be true, you should have a bivalent functional group. Is double bond necessary? No. Is triple bond necessary? No. What is necessary? A bivalent functional group. That is how you can solve it. I hope it is making sense to all of us. Okay? Alright. Alright. Let's continue. Let's move to the next question. I hope this one is clear and try to understand everything related to it. I am not going to solve only the question. I will tell you the concept behind it so that if you see any other question similar to it or they ask you any other concept similar to it, you can answer that also. This is the point of solving past year questions, not memorizing the answers. Okay, don't think that if I solve past year questions, I will memorize it and they will ask me the same question again. Maybe they will, but the idea is you are trying to understand the concept behind it. Okay, See the next question. The IUPAC name of this compound is. How do we write IUPAC name of a compound? First, we will select the main carbon chain. How do we select the main carbon chain? My main carbon chain must have maximum number of carbon atoms. Great. This is the case for saturated compound. What if we have double bond or triple bond in our compound? For example, in this one, we have unsaturated system, right? So we will select such a carbon chain which has these multiple bonds also present. Maybe the length of the chain is less, but if it contains multiple bonds, we will select that to be our parent chain. Okay, so keep that in mind. Okay, what if functional groups are present? Then you will give priority to the functional groups. You will select such a carbon chain in which functional groups are present, although the number of carbon atoms in that chain is this. So you have to choose the parent chain based on the compound given to you. So this is a unsaturated compound. In this case, we will give priority to our multiple bonds. Okay, so try to expand this structure. You may think that I will start from here. I will expand it so that you don't get confused here. This is how you can write it. These three methyl groups which are written here, these are substituents, right? If you want to expand it, it will look like this. Okay, next. Now please notice this C2H5 that is written here. I can expand it to CH2, CH3, right? I'm not doing anything wrong. I am expanding it because otherwise you will not see it and you will select this to be your parent chain. That would be wrong. Why are we not selecting this to be a parent chain? It has 8 carbon atoms. It has multiple bonds. Because please see, you can select this one also, right? How many carbon atoms are present in this parent chain? 9 carbon atoms. It contains multiple bonds also. So why will we select one which has 8 carbon atoms? That would be wrong. This is the correct representation. Now the second question that you may ask, why am I starting the numbering from this side? Why not from here? Let's see which one is correct. I'm just telling you which one is our parent chain. The numbering part we will decide now. Okay. So I will do the numbering with a different color so that you can differentiate. Okay. I have done the numbering from right hand side. Let's do the numbering from left hand side and then we will decide which one is correct. Okay. So now I am doing the numbering from this side. I should write it here. This was 8, this was 9. And now let's do it with a different color. Okay. So first carbon atom, second, third, fourth, fifth, sixth, seventh, eighth, ninth. Okay. So if I do the numbering from this side, how will we select which one is correct? I should give the lowest locant numbering to my multiple bonds and after multiple bonds to my substituents. Okay, so multiple bonds will take precedence here because it is an unsaturated compound. Okay, so if I start the numbering from left hand side, you can clearly see my multiple bond comes at 3rd position. But if I start the numbering from the right hand side, my multiple bond comes at 4th position. So which one would be correct? I have to give them the lowest possible number, lowest locant numbering we have to do. So I have to select the green chain. I have to select the numbering which I have done from the left hand side, not the right hand side. And based on that, we will write the name. So total, how many carbon atoms are present in the parent chain? 9. See the options now. In which case, do you see 9? Nonadiene, this could be correct. 7 carbon atoms, leave this. 8 carbon atoms, leave this. Again, 7 carbon atoms, leave this. So you don't have to see where your substituents are present. Based on the number of carbon atoms in the parent chain, you can decide your correct answer. But we have learned something extra also, that from which side we will do the numbering. Let's cross check whether we have done the numbering correctly or not. Otherwise, it is not required for this question at least, because you can give the correct answer just by counting the number of carbon atoms. That is all you have done. Okay, so I can see on second position, this is the correct one. Okay, forget about the red numbering, that is wrong. So on second position, I have a methyl group, and on seventh position, I have the methyl group. So 2,7 dimethyl. Any other substituent you see here? No. What about the multiple bond? I have two multiple bonds at third position and at sixth position. Is it? Okay, sorry. Third and fifth. I'm so sorry. Yes, I have multiple bonds at third and fifth position. We have to select the fourth carbon atom. Okay, so this one is correct, right? 2,7 dimethyl 3,5 nonadiene. This will be our correct answer. I hope it is making sense to everyone. So this is how you have to answer. You have to select your parent chain first. That must contain maximum number of carbon atoms, and in case of unsaturated compounds, it should contain your multiple bonds also. Okay, so this will be our correct answer. All right. Now let's see the next question. I hope this one is clear. Okay, let's wait. Yes, species A, B, C, D formed in the following bond cleavages respectively are. You have learned about two different types of bond cleavages. I hope you remember homolytic bond cleavage and heterolytic bond cleavage. I will tell you once more. Okay. Yes, so we have homolytic bond breaking and heterolytic in homolytic bond breaking, the two groups will take one electron each, so it will give rise to free radicals. Okay, homolytic, both of the groups will take one electron each. There is equal distribution. What happens in case of heterolytic bond cleavage? In this case, one of the atom, one of the group, one of the species is electronegative. So the electronegative atom has the property to keep the shared pair of electron towards itself. So let's say B is more electronegative than A. So B would try to keep the electron density towards itself. So B will take the electron density and A will get nothing. Okay, so this one will be heterolytic bond breaking. It will generate a cation and an anion, and this is what they are asking you. So in case of heterolytic bond breaking, the more electronegative atom generally will take the electron density with itself. It will become negatively charged, and the electropositive atom will become positively charged. And the same species you can break homolytic also if some kind of radical generator is given to you in the equation. For that, you have to see the reagent provided. We don't have to worry so much. For us, what is the question? Please see the question now. They have given you the type of cleavage. They are just asking you what is A and B, C and D. They have given you the arrow also, which one is taking the electron density. So we are doing heterolytic bond breaking here. Okay. So in this case, iodine is taking the electron density as they have shown us with the curved arrow also. So iodine will become negatively charged and the alkyl group will become positively charged. So we will write it like this: CH3, CH2 plus I minus. Such a simple answer. What about this one? In this case, they are saying that alkyl group is taking the electron density because it is much more electronegative than copper. Okay, we can do that also. So CH3, CH2 minus, the one which takes the electron density gets the negative charge and the other one will become positively charged. I hope it is making sense to all of you and you are done. Okay. So what would be our correct answer? What is A, B, C and D? CH3 CH2 positive, I minus, CH3 CH2 minus, Cu plus. This is a correct answer. Option A only, and you are done. That is how you have to solve it. I hope it is making sense to everyone. This is how they're asking you the questions. If you understand homolytic and heterolytic bond breaking, you can easily answer this question. Okay. Now, let's see the next question. Assertion, carboxylic acids are more acidic than phenols. Okay, this statement is true, and we are going to see the resonating structures also. Okay, what is the reason? Resonance structures of carboxylate ion are equivalent, while resonance structures of phenoxide ion are not equivalent. That is the reason. In the last session, which we have done for GOC, I have told you the priority order of stability factors. I have told you. I hope you have noted it down. I will tell you once again, but please revisit that session also. Solve the question that we have done there also and revise the concepts once again. So I have told you this order. Equivalent resonating structures will provide greater stability than non-equivalent resonating structures or simple resonance. And after that, we will have hyperconjugation. And in the very end, you will have inductive effect. Inductive effect is the weakest effect. So we have discussed all these electronic effects in the last session. I hope you have seen that. So based on that, now can we answer this question? Both assertion and reason are true. Yes, carboxylic acids are more acidic than phenols. The reason being that the carboxylate ion are going to show equivalent resonating structures, while phenoxide will show non-equivalent resonating structures. So both the statements are true, and your reason is the correct explanation of assertion. Both assertion and reason are correct, and reason is the correct explanation of assertion. I will show you the resonating structures also so that you can remember what we are trying to say. Whenever they ask you any question based on comparison of acidic strength, based on comparison of basic strength, I have told you this thing also. If you want to compare acidic strength, you will see the stability of conjugate base. Stability of conjugate base increases acidic strength increases. And how do we understand what is conjugate base? The species which is formed by removal of a proton is called as conjugate base. Okay, so you have your carboxylic acid. Okay, now I want to form conjugate base of this carboxylic acid. So I will remove a proton and that will become a conjugate base. Now this conjugate base, this carboxylate ion that you have written here is resonance stabilized. How? This negative charge can come here to make a double bond, and that double bond can shift to the oxygen atom and become negative charge. So this will generate these two resonating structures. These two resonating structures are equivalent, right? They are similar to each other. So if you have equivalent resonating structures, it will provide you extra stability. This is what we are trying to say here. What about phenoxide ion? What happens in case of phenoxide ion? That is also resonance stabilized. It is, but it does not give you equivalent resonating structures. Let me show you. This is your phenoxide ion after removal of a proton. Okay, there is a resonance here also, and here the resonance is with the benzene ring. So you will have multiple resonating structures, but none of them are equivalent. Okay, so this negative charge will come here, double bond will shift here. Now this negative charge will come here, double bond will shift here. Okay, What is next? Okay, finally, you will get your phenoxide ion once again. So how many resonating structures you have drawn? 5. So if I have 5 resonating structures and if you compare it with 2 resonating structures, this must get precedence because I am stabilizing it more. You are correct. But in this case, all the resonating structures that you have drawn are non-equivalent. They do not resemble each other. So who will be your winner? The one with 2 resonating structures although, but they are equivalent. So always remember, equivalent resonating structures will provide greater stabilization to the conjugate base than non-equivalent resonating structures, and that is why we say carboxylic acid has higher acidic strength than your phenols. And your question is done. Okay. So I hope this is clear, and note this down, remember it, at least the order. You have to remember, you have to apply that. Okay. So this one is correct. Let's see the next question. You have to arrange the following in decreasing order of their basicity. What I have told you about basicity, first thing, what do we call as a strong base? The one which can donate the lone pair of electrons easily. So if you can donate the lone pair of electrons easily, you will become a strong base. For that to be true, your lone pair of electrons must be localized on the atom. It should not move within the atom. You have the electron density. You don't want to give it to anyone else. Then what is the point of that electron density? You will not be called as a strong base. You have the electron density. You want to donate also. Then you will be called as a strong base. So keep that in mind. Delocalized lone pair of electrons, less basic strength. Localized lone pair of electrons, higher basic strength. Okay. I will write it here. Localized lone pair. What is localized? That is present on that atom only. It is not moving within the species. Delocalized, that is moving within the species. That is part of resonance. Okay. So if you have a localized lone pair, it will provide higher basic strength. Why? Because then the lone pair of electron is available for donation. Okay. So this one will have higher basic strength. This is what we are trying to write. So you just have to say in which case the lone pair of electrons is localized. That would be considered as a stronger base. Okay. So in this case, if you notice, you have the lone pair of electrons on NH2. Is it in conjugation with the benzene ring? No, it is far away. It is localized on nitrogen only. It is not participating in resonance. But if you see this one, this is part of delocalization, right? If it is delocalizing, then it is not available for donation. So it would be considered as a weaker base than B. Okay. What about this one? In this case also there is delocalization. Yes. So both of them would be considered as weaker bases. But how do we compare between these two? So you have to see what type of group is attached now. This is an electron donating group. This is an electron withdrawing group. And I have told you this thing also. Basic strength depends upon stability of conjugate acid, which is a positively charged species. And how do we stabilize something which is positively charged? We have to make it neutral somehow. How do we neutralize it? By attaching some electron donating group to it. So electron donating groups will stabilize it and electron withdrawing groups will destabilize it. So if you remember this order, you can easily answer. So what type of groups will favor us? Electron donating groups. What type of groups we have to stay away from? Electron withdrawing groups. Come back to the question. This one is electron donating, good for us. This is electron withdrawing, we want to stay away. It will withdraw the electron density. If it withdraws the electron density, how will we donate it to someone else, right? So this one is most basic because here we have a localized lone pair of electrons. In these two cases, there is delocalization. How we compared between the two? By seeing what type of group is attached. So this one had electron donating group, higher basic strength, then option C. This will be the correct answer and you are done. BAC option B. Okay. So this is how you solve any question in which they are asking you to compare the basic strength. We have done something similar to compare the acidic strength. I will write that order also once again. Please note it down. For acidic strength, you have to compare the stability of conjugate base. Which will depend upon electron withdrawing group, and we have to stay away from electron donating group. Okay, so we are doing the reverse. If you understand these two things, you can answer any question related to comparison of acidic strength, comparison of basic strength. Okay, see the next question. I hope this is clear. Please note it down. It will help you immensely in multiple different questions. Okay, all right, let's see the next question. From the following, identify the groups that exhibit negative resonance minus R effect. You have to identify electron withdrawing groups when attached to a conjugated system. So you have to identify what type of groups will show electron withdrawing effect. We have covered this also. What type of groups will show electron donating effect, which have lone pair of electrons, which have the electron density. If you don't have anything, you will not give it to someone else. Obviously, if you have something extra, then only you will think about donating. Right? So electron donating groups will be electron rich. Maybe they will have a lone pair of electrons, maybe they will have a negative charge. Electron withdrawing groups on the other hand will be electron deficient. So maybe you will see a multiple bond is present. Maybe there is some positive charge. You will call all such groups to be electron withdrawing. So in this case, what are they asking us? Electron withdrawing groups. So what we have to look for? Multiple bonds of positive charge. Multiple bond between less electronegative and more electronegative atom, or you may look for positive charge. Partial positive charge will also work. If you see any of these things, you will say this is an electron withdrawing. Okay, so now please see, this is for my CHO. Do we see a multiple bond between less electronegative and more electronegative atom? I can see carbon is less electronegative, oxygen is more electronegative. So is this an electron withdrawing group? Yes. So this is electron withdrawing. Good for us. What about amino group? A lone pair of electrons is present. It has extra charge density. So what do we call such compounds? Electron donating groups. So whenever you see a lone pair of electrons on negative charge, you will call it to be electron donating. Okay. Then we have cyano. Do we see a multiple bond between less electronegative and more electronegative atom? I can. And this one is also electron withdrawing. What about nitro? Do we see a multiple bond between less electronegative and more electronegative atom? Yes. So is this also electron withdrawing group? Yes. So I hope you understand. You don't have to cram everything. If you understand this feature, you can easily answer. I will write something for electron donating group also. You will find a lone pair of electrons, or then you will call such compounds to be electron donating groups. So in this particular case, okay, I have something else also. Alkoxy. Let's write this also. OR. Lone pair of electrons, electron donating group. So this is electron withdrawing, electron donating, withdrawing. So how many of these will show minus R effect? Electron withdrawing groups. So I can see option A, option D, option E. A, D and D. Simple. So do we have to know each and every group? They can give you some new group also, although they don't. They repeat the same functional groups again and again. But you should have some idea in your mind. What are we looking for? We are looking for multiple bonds or positive charge or partial positive charge. Multiple bonds between less electronegative and more electronegative atom. Not similar kind of atoms. Remember that also. Then we will call all such compounds to be all such groups to be electron withdrawing groups. Okay, so this is our correct answer. Arrange the following in the correct order of their acidic strength. So what I have told you about comparison of acidic strength, you will compare the stability of conjugate base. What do we mean by conjugate base? The group which is formed after the removal of a proton. So in this case, you will form some kind of phenoxide ion, substituted phenoxide ion. Then how do we compare the stability of that phenoxide ion, that conjugate base? We will see whether it has electron withdrawing groups attached to it or electron donating. Electron withdrawing groups, good for us. Electron donating, we will stay away. Okay, so we will write this here once again. Is directly proportional to the stability of conjugate base, which is directly proportional to electron withdrawing groups attached to it. And what type of groups we have to stay away from? Electron donating groups. So in this case, I don't have anything. So there is hydrogen. We don't have to worry about this. Okay, this is electron donating group, alkyl group. It will show plus I effect. Okay, what about NO2? You have just now seen it, electron withdrawing group. Okay, we want electron withdrawing group, they are good for us. NO2 again, but see the position of that NO2 group. At meta position, mesomeric effect is not shown. What type of effect is visible? Minus I effect. And if you have to compare between mesomeric effect and inductive effect, obviously mesomeric effect will take precedence. I have told you this thing. Mesomeric or equivalent resonating structures over hyperconjugation, then in the end inductive, right? So in this case, it is electron withdrawing group, but it is showing only minus I effect. It is stabilizing, but the strength is less. This is also stabilizing, but the strength is more because you have mesomeric effect here. Okay, and in this case, you will have hyperconjugation and inductive, but both of them are destabilizing. And in this case, we are not seeing anything. So it will be better than this one at least, because we have to stay away from electron donating groups. So if I want to write the order, in which case your conjugate base is more stable, in which the strength of the electron withdrawing group is more. So this one. Fourth is most acidic, then third, then first, because I don't see any effect here, and finally second. Fourth, third, fourth, second. Option B. This is how you have to answer. Now we have solved multiple questions based on the same exact concept. I hope you are noting it down. Okay. Now let's see the next question. In which of the following hyperconjugation is not possible? See, hyperconjugation involves the delocalization of sigma bond electrons with the empty p orbital. Delocalization of sigma electrons with empty p orbital. This is what we mean by hyperconjugation. And what are the conditions we are looking for? First of all, it is visible in case of carbocation, in case of free radical and your alkene system. So your hyperconjugation can only stabilize carbocation, free radical and alkene system. Please don't apply it to carbanions. They do not have empty p orbitals. You will not see hyperconjugation there. Okay, I will write this. Hyperconjugation stabilizes carbocation, carbon free radical and your alkene system, not your carbanion. There is one such question that was asked, that in which case hyperconjugation is possible. In these three cases, yes, but not in case of carbanion, because you don't have any empty p orbital in case of carbanion. Okay, first of all, you have to keep that in mind. Now let's come to the question. So in this case, I have the alkene system. Great. What are the conditions for hyperconjugation? Based on whatever group you are studying, carbocation, carbon free radical or the alkene system, you have to first see, do we have some alpha carbon atom, that is sp3 hybridized? What are we looking for? Alpha carbon atom. What is the hybridization of that alpha carbon atom? sp3. Can we look for sp2 or sp? sp3 hybridized carbon atom must be there, and that sp3 hybridized carbon atom must be attached to at least one alpha hydrogen. Then only you will say hyperconjugation is possible. I will write down the conditions. sp3 hybridized alpha carbon atom. Great. And in addition to that, if you see these two conditions are followed, then only you will say yes, hyperconjugation is possible. Okay. So in this case, we have alkene system. This will become our alpha carbon atom. Do we see any alpha hydrogen is attached to it? This carbon is alpha carbon atom. It is attached to 3-methyl groups. I don't see any alpha carbon atom. Will it show hyperconjugation? No. So this is our correct answer. What about this one? This is my alpha carbon atom. I have at least one hydrogen. This one will show hyperconjugation. Okay. What about this one? This is my alpha carbon. It is attached to 2 alpha hydrogens. This is my alpha carbon. It is attached to 2 alpha hydrogen. I need at least one. Then only I will say hyperconjugation is possible. Greater the number of alpha hydrogens, more will be the stability of your intermediate species. Okay. So in which case you will not see any hyperconjugation? Option A. And you are done. So you just have to know what type of groups will show hyperconjugation first. And second thing, we have to follow these two conditions, and then only your answer will be correct. Okay. See the next question. Identify the molecules which have sp hybridized carbons. See, if you are given any organic compound, there is a direct way to find out the hybridization. You will look at that carbon atom and see how many alpha bonds, you will see how many sigma bonds are made by that carbon. Okay, sigma bonds. So how to identify the hybridization of any carbon atom that is present in your hydrocarbon? You will look for number of sigma bonds made by it plus number of lone pairs. That will give you the steric number. Based on that, you can decide the hybridization. So steric number is number of sigma bonds plus, what are we looking for? Lone pairs. So if you count these two, you can decide what is the steric number. And if you know the steric number, you can decide the hybridization. If steric number comes out to be 4, sp3. It comes out to be 3, sp2, 2, sp. So in this case, we have to identify how many of them have sp hybridized carbon atom. I have written everything. You just have to draw the structure of compounds. Okay. So first one is ethane nitrile. Look at this carbon atom. It has 2 sigma bonds. We have to count only sigma bonds, not pi bonds. I'm not talking about pi bonds here. Okay. So it has 2 sigma bonds. This is sp hybridized. So do we have something which is sp hybridized? Yes. Second, buta-1,3-diene. Okay, this one is sp, this one is sp2, again sp, and then sp2. Okay, so do we have sp hybridized carbon atoms? Yes, we do have sp2. No, we are looking for sp, not sp2. All right, leave this. This is sp2, this one is sp2. So we don't have any sp hybridized carbon atom. Second is not counted. Propa-1,2-diene. What is the hybridization of this carbon atom? sp. It has only 2 sigma bonds. I don't see any lone pair of electrons. What about this one? It is connected with 3 sigma bonds. So sp2. 3 sigma bonds, sp2. We are looking for sp hybridized carbon atom. Yes, it is present. Okay, so in this case also we have sp hybridized carbon atom. In this case also ethyne. I have 2 sigma bonds here, 2 sigma bonds here. Please understand. The first bond that is formed between two atoms is always sigma bond. So if you have a single bond, sigma. If you have a double bond, sigma plus pi. You have a triple bond, sigma plus 2 pi. Okay, I will write it here. Single bond, sigma. Double bond, sigma plus pi. A triple bond, 1 sigma plus 2 pi. Okay. So in this case, I have 1 sigma plus 2 pi bonds. And there is 1 sigma with this hydrogen also. It is sp hybridized. Okay. What about this one? Benzene. All of them are sp2 hybridized. Are we looking for sp2 hybridized carbon atom? No, we are looking for sp hybridized carbon atom. So this one has sp hybridized carbon atom, this one, and the first one. So first, third, and fourth. First, third, and fourth, option D will be our correct answer. That is how you have to answer. Please remember that. Steric number, number of sigma bonds plus lone pair of electrons. I don't see any lone pair of electrons, so we are not counting that. Maybe in some compound there is a lone pair of electron or negative charge. Please count it. Okay. So this part also we have done in the last session. Now we have solved the question also. Okay. Yes, X-Blade Gaming, you have to solve more questions. Obviously, we have done 2 sessions on this chapter only. In the first session, I have told you the concept also. We have solved questions after that. And in this particular session, we are just solving questions provided you have revised the concept. So after this session, yes, you have to practice more questions, but I am telling you all the concepts that have been asked. Okay? But obviously, practice more. All right, let's see the next question. Consider the following carbocations and arrange the above carbocations in the order of their decreasing stability. How do we compare the stability of carbocation? Same thing that we have done so many times. We will see whether the carbocation is stabilized by resonance or hyperconjugation or inductive effect. Which one will take precedence? Resonance. After that, hyperconjugation. In the end, inductive. Okay, inductive is the weakest effect. Okay, I will write it once again. First, look for resonance. This is the priority order of strength. Okay. Priority order. Resonance, then hyperconjugation, and third will be your inductive effect. Resonance, hyperconjugation, inductive effect. Okay. So in this case, we have resonance. It is connected to your phenyl ring. Please see. So this one is most stable. Okay. Followed by, in this case, what about this one? You have a double bond attached to your carbon atom. So this particular carbocation is sp hybridized. Is it stable? If I compare it to sp2 hybridized carbocation, obviously no. Okay. So please see, this will be your stability order, sp2 over sp. Remember that. Okay. So in this case, I have sp2 hybridization, much more stable, sp hybridization, less stable. What about this one? This is also stable because of hyperconjugation. Okay. In this case, you have resonance. In this case, you have hyperconjugation because of 6 alpha hydrogens. These two are my alpha carbons. I have 6 alpha hydrogens. But hyperconjugation is weaker than resonance. Also remember that. What about this one? I have 3 alpha hydrogens. So if I want to write the stability order, at the first position I will have resonance because of the phenyl ring. Then hyperconjugation because of 6 alpha hydrogen. Then 3 alpha hydrogens. And finally, sp hybridized carbocation. Okay. So your correct order will be first, then third, then fourth, and then second. First, third, fourth, second. Okay, we have one more. In this case also, I have only one one sigma bond. Okay, so this one is less stable. So in the end, we will have fifth. It is even less stable than second because here at least I have a double bond. Here I have a triple bond. Okay. All right. Now, the correct order is first, third, fourth, second, fifth. First, third, fourth, second, fifth. This is the order of stability of your carbocations. Please see what is the hybridization first. After hybridization, what type of effect is shown? If you have sp2 hybridization, it will be much more stable than sp, obviously. A positive charge is present on a less electronegative species is much more stable. As the percentage S character increases, electronegativity increases, stability of carbocation decreases. If you have a negative charge, great. If you have a positive charge, stay away from it. Okay, so this will be your correct answer. First, third, fourth, second, fifth. Yes. All right. So, Charan, option A. Yes, option A is correct. Yes, yes. Okay. All right. Let's see the next question. The electron displacement effect observed in the given structures is known as. They have told you that you have some kind of electron displacement effect taking place. They are just asking you whether it is electron withdrawing or electron donating. Okay. So what type of group is there? Do we see a multiple bond? A multiple bond between a less electronegative and a more electronegative atom. Then what do we call such species? Electron withdrawing groups. So is this an electron withdrawing group? Yes, it is an electron withdrawing group. So what type of effect will be shown by it? Minus R effect. And you are done. That is all you have to do. They're just asking you what type of effect is shown by this particular species. They are not asking you to compare also. They have shown you the electron displacement also. They have helped you so much. You just have to visualize what is happening. A multiple bond is present. A multiple bond between less electronegative and more electronegative atom will lead to electron withdrawing effect. That is minus R effect in this case. Okay. Okay, this was simple. The number of activating and deactivating groups, again, we understand the background. How we know activating groups? Activating groups are electron donating groups. Deactivating groups are electron withdrawing groups. So activating groups, electron donating groups must have a lone pair of electrons or some kind of extra charge density. Okay. So please see. Do we see a lone pair of electrons? Yes. In this case, a multiple bond. So in case of a lone pair of electrons, you have something extra. You can donate it to someone else. So you are an electron donating group in that case. This one is electron withdrawing group. This one is electron donating group. Again, electron withdrawing. Again, electron withdrawing. So if you see a multiple bond is present, then you will call it a electron withdrawing group. You see a lone pair of electrons, a negative charge, you will call it an electron donating group. I have already told you this thing. I have written it down also. I hope you can understand this question. Okay. So this is the same thing that we are repeating. If you understand the concept, so many different questions can be asked from you. Okay. So in this case, the correct answer is electron donating groups are 2. Electron withdrawing groups are 3. Option A, and you are done. They're just asking you to calculate how many are there. They're not asking you to compare the strength also. So good of them. Okay. If they ask you to compare the strength, you have to know that also. Okay. See the next question. Arrange the following free radicals in the correct order of their stability. So radicals are also electron deficient. So if someone is going to donate them electron density, they will be stabilized. If you see hyperconjugation is there, you will say that it is stable. Number of hyperconjugating structures possible, that will increase the stability. Simple. Okay. So in this case, it is connected with a double bond. Leave it. This will be present somewhere in the end. This one. How many alpha hydrogens are there? 6. What about this one? I can see 9 alpha hydrogens. So which one will take precedence? 9 alpha hydrogens, obviously. What about this one? Do we see hyperconjugation there? I don't have any alpha carbon. It is just carbon with 3 hydrogens. Hydrogens will not do anything. But at least this is sp2 hybridized. That is good for us. Okay. It is not connected to a double bond at least. So it is much more stable than the forced one. Okay. So what would be the correct order? 9 alpha hydrogens. Third, second, and then in the end first. Fourth, third, second, first. Option B will be the correct answer. Okay. Alright. So I hope it is making sense to everyone. Alright. Let's see the next question. The delocalization of sigma electrons of carbon hydrogen bond of an alkyl group with the pi electrons of benzene is observed in delocalization of sigma electrons of carbon hydrogen bond of an alkyl group with pi electrons of benzene. So we are talking about whenever you see delocalization of sigma electrons. In inductive effect, there is no delocalization. It is just polarization. No one is moving anywhere. In inductive effect, there is no bond breaking. Okay, so leave inductive out of the question. Then in case of resonance, there is delocalization, but of pi bonds, of lone pair of electrons, not sigma bonds. So we can leave resonance also out of the picture. Okay, what is left now? Hyperconjugation. In case of hyperconjugation, there is delocalization of sigma bond electrons with empty p orbitals. In case of carbocation free radicals or pi electrons. Okay, so correct answer is option B, hyperconjugative effect. Okay. Correct order of acidity once again. How do we compare the acidic strength? Stability of conjugate base. How do we compare the stability of conjugate base? Based on the carbon ion you have formed, or in this case the phenoxide ion you have formed. So how to stabilize something which is negatively charged? We are going to attach it with some electron withdrawing group. Electron withdrawing groups are present, acidic strength increases. Electron donating groups are present, acidic strength decreases. Okay, so in this case I don't have anything good for us. Electron donating group, we don't want it. Electron donating group, we don't want it. But see the comparison. This one is going to show plus M effect, a stronger effect. This one will show hyperconjugation effect, a weaker effect. So there is destabilization by a strong group. We will stay away from it. There is destabilization by a weaker group. So this one will take precedence. Okay. So if you compare the acidic strength, this one is most acidic, followed by this one, because at least we have only hyperconjugation, and in the end, third. This will be our correct order. That is how you can compare the acidic strength. Same exact concept. Stability of conjugate base. How do we compare the stability of conjugate base? By attaching some electron withdrawing group to it, because it is a negatively charged species. That is all you have to do. Okay. So I hope this is clear. I hope this is making sense to everyone. Any doubt, any questions so far? So like that, we will continue with more questions in the next session also. Okay. One last question, then we will end the session. Okay. Which one of the following methods can be used to find out the percentage composition of halogen present in the organic compound? So you have learned about different types of estimation methods based on the group you are trying to estimate. Carbon, hydrogen, nitrogen, sulfur, you have your halogens. So if you are trying to find out how much amount of halogen is present, what type of method you use there, at least know the method. Carrier's method. Dumas method is used for estimation of nitrogen. Zeldal method also for nitrogen. Lassinez method is used for nitrogen, sulfur, phosphorus, and your halogens. Okay, so not this, not this, not this one. Carrier's method is our correct answer. Okay, so they can ask you question based on what type of method you are using to estimate also. Just the name of the method and your task is done. Okay, so I hope this is clear. That is all for today. We have a few more questions which would be made available to you on our Telegram channel. You can solve more questions and practice more and more questions, then only you will perform well in the examination. Don't just leave it to the questions that we have done here. You have to practice more questions. You have to build your confidence. Okay, so let us end our session. One last piece of information. So if you have your brothers and sisters who are studying in grade 3 to 10, they can enroll in our maths 1-year program. It is just for ₹999 and all IIT, NIT faculty would be teaching you. So we will cover all the CBSE, ICSE and state board syllabus. And in addition to that, you can take help of Sysya AI also. So you can do text to text, speech to text, and image to text doubt solving there. So you can scan this code, download our app, and the course will start from 5th May. So I hope you will join that. And we will continue with our EAPCET series in the next session, in which once again we are just going to solve questions, past year questions, so that you can practice more. So try to revise all the concepts that we have already done and focus on solving questions from now. Okay, so that is all from my side. I hope you like the session. Stay tuned. We will solve many more questions in the next class. Bye everyone. Have a great day.